So my next goal is to talk about a proof by contradiction, which is our next type of proof strategy that we're going to use. So in this is something that we've already used a few times over the semester. So for example, proving that the real numbers between 0 and 1 are uncountable. We did this using a proof by contradiction. So the way that this works is that to prove a statement is true, so to prove a statement is true, what we'll do is assume it's false. This is a slightly strange strategy, but it's logically sound. So if we want to prove that something is true, what we could do is assume that it's false and then deduce a contradiction. And so essentially what we're doing is we're saying, well, if it's false, this contradicts something else that we know is true. Therefore, it must be true, which is a slightly strange game. But let me say that one more time. Assume that the statement is false. Show that if the statement's false, that actually leads us to a contradiction. And therefore, that means that it couldn't have been false. The original statement must be true. Okay, so that's our strategy. So what I want to do is an example or two with proof by contradiction. And I want to start with something where, let's say, let x be a rational number and y an irrational number. So y is going to be a real number that's not rational. What I want to do is I want to prove that x plus y is irrational. In other words, the sum of a rational and an irrational number is irrational. What we can do is, if we're going to do a proof by contradiction, what we're going to do is we're going to assume that the statement is false. So assume that the statement is false. For a contradiction. And I like to actually write in the word contradiction in the first sentence just so that it's clear. Again, this is leaving that breadcrumb trail that I like to talk about. So I want to assume that the statement is false for a contradiction. I like to just make it very clear to the reader what our strategy is, how this is going to work, and where we're going to go from here. So we're going to assume that the statement is false in order to deduce a contradiction. Let's think about what this means to be false. And so what I want to do is I want to think about, we have to kind of put together all of the logic that we know, everything that we've talked about so far. I want to kind of think about this and break this proof down by just first thinking about this in terms of pure logic. So I want to think of the statement as an implication statement. And the statement is that if x is irrational and if x is, I think I just misspoke. If x is rational and y is irrational, that implies that x plus y is irrational. Okay, so I'm thinking of this just as a P implies Q statement, where this is our P and this is our Q. And so what does it mean for this statement to be false? Well, an implication is going to be false if this first part is true, but the second part is false. Okay, so remember that when we talked about the logic tables for the implication statement, the implication is false only when the hypothesis is true, but the conclusion is false. So that's what we'll do in our case. So the way that we're going to start this, and I'll move this around so that this proof looks a little prettier in the end. Maybe we can just move this down and out of the way, but that kind of tells us what to do next. So we're going to assume that x is rational, y is irrational. So in order, again, just to break this down one further step, in order to assume that this statement is true, this is an and statement, so that means both statements have to be true. So we're going to assume that x is rational and y is irrational. And then we're going to assume that q is false. So in other words, x plus y is not irrational, but rational. So we're going to assume that x is rational, y is irrational, and x plus y is rational. Okay, so again, just breaking it down into the logic, I think really helps us figure out why we've made these choices that we've made here. So that's what we're going to do. And then now we have to find some contradiction. And the contradiction is that, well, if x and x plus y are both rational, then there exist integers a, b, c, and d, so that x is a over b and y is c over d, where b and d are non-zero, if you want to write that out. And then, I'm sorry, not x, but x plus y. Then y, which is x plus y minus x, is going to be a difference of two rational numbers, which means that it's a rational number. This is bc minus ad. So that y is rational. But that's a contradiction because we assumed y was irrational. Okay, so this contradicts our assumption that y was irrational. And that's enough. Okay. Sorry for the pause. I had to sneeze. Okay. Now immortalized on YouTube. Anyways, so we assumed that x was rational, y was irrational, and yet x plus y was rational. And then from that, we found a contradiction that y, where are we? Y was rational and irrational at the same time, which can't happen. So that means that our starting assumptions can't work. They're not consistent. They don't work. And therefore, therefore, the statement can't be false. Okay, that's not possible. It must be true. It must be that if x is rational and y is irrational, then x plus y is irrational.